Hey everyone, this is Joseph Miano and we are Team 5. Our topic is understanding graceful degradation through the parallel distributed processing framework. In this project, we model sensory damage and brain damage in neural networks via audio data and image data modalities. Now we'll go through a demo of our project. First, the imports. The way this will be structured is first we'll go through the image models and then the audio models. So for the image models, we first define the dataset and load the dataset. You can see some examples of our two classes here. This represents the clean data. Then we have the data with noise added. And the reason we have noise is we have two different types of inputs to model sensory damage. So when we have clean inputs, that represents no sensory damage. And when we have noisy inputs, that represents sensory damage. And you can see that these inputs are passed through our AlexNet to generate predictions. Here we load the model, and here we obtain model outputs. So on the left, we have predicted values, and on the right, we have the ground truth. So when they match, it means the model is predicting correctly. Here's an example of the pruning that we do. So before I mentioned the noise added to model sensory damage, the pruning models brain damage. So we remove weights from the network, we prune them, and that's modeled here with this code. And here's an example of the pruned model output. So next, the audio data. So again, we define our data set, load our data set. Here are some examples we can go through of what the data sounds like. That's a clean siren. That's a siren with noise added. And that's a jackhammer. So then we define our model architecture. So we have two different models for the audio data. We have the raw model, the raw audio model, and the spectrogram model. So this one takes raw audio as input, passes it through a neural network, and then creates a prediction label. We load it here, and again, obtain some model outputs. Next is the spectrogram model. So the difference here is that instead of passing raw audio into the network, it first transforms it into a spectrogram. And there's some examples of spectrograms shown here. Spectrogram is just an image representation of a sound signal. You can see there's three classes of noise. What we did here, we have the clean, we have the noisy raw, which means noise was added to the raw data before it was converted to a spectrogram, and then noisy class where the noise was added to the spectrogram itself. We define our model architecture. This model architecture is very similar to the previous one, except we have this pre-processing step for the spectrogram. We also use 2D convolution and processes instead of 1D. So we load our trained model. Again, we can obtain model outputs from our trained model. And we can also do pruning of our audio model. And finally, we developed 3 different cognitive architectures based on these results. And we do encourage you to view our full paper for more details on this project. Thank you for listening.